Hello, my name is Chi Amaka,
And I'm Olivia.
and we're going to be talking about time domain nodal analysis, which is going to be purely resistive. To understand this, you must understand Kirchhoff's current law, which states the algebraic sum of all currents entering and exiting a node must equal 0. So with this picture, you can see that I1 and I2 are going in, and I3 and I4 are going out. So we can see that I1 plus I2 must equal I3 plus I4.
Now that you know that, you might want to ask yourself, what is a node? A node is a region between two or more circuit elements. Now, this is important because it's not necessarily every junction is a node. It has to just be between two circuit elements. So if you see in this example, you might think that this node here and this node here are separate nodes. So this one, the pink and the purple. But if we redraw it, we can see that this is only one node altogether because this resistive element goes and connects to these two different elements in one time. Additionally, this bottom node, you might think there's three separate nodes because there's three separate dots, but they're all equal to one node because there's no type of circuit element in this part at all.
For nodal analysis, it is important to understand Ohm's law because that is how we're going to represent our currents. So we have that V equals IR, and so how it's going to be rewritten is I is equal to V over R. So we're going to take the voltages and divide them by the resistances. Let's look at one example. We're going to use two different methods to solve this example, and you can use either one. For the question, we're going to try and find the voltage across two resistors, and we're going to set the bottom part as the ground node because there are just a lot of branches going to that particular node. It will simplify our entire problem. Let's look at the first method. The first method is really going to emphasize on the KCL, and it's going to really look at I1, the currents going into each respective node. Now, for node 1, remember that we're going to have that the I1 is going to the node just because the voltage is going from negative to positive, so we want to represent the current the same way. And then we can also see that this 2 amps is going into node 2, and it's probably going to split off, and so we're going to have I2 also going to node 1, and we're going to have I3 going towards the ground because it needs to go through that last resistor. Then for node 2, we have 2 amps going in, I2, as we said, goes towards node 1, and I4 goes down towards the ground. Now, let's represent them with their current equations. For node 1, we have, as we said, I1 and I2 going in, which is going to be equal to the I3 going out. And then for node 2, we're going to have the 2 amps going in, which is going to be equal to I2 plus I4 going out. Remember, for these, you have I is equal to V higher minus V lower over the resistance. For that, you know that if the current is going this way, since there is a resistor in the middle, we know that this side must be higher and this side must be lower due to the voltage going through that voltage drop. Remember this whenever we're writing our equations. So for node 1, we're going to start off. For I1, we're going to have 12 minus V1 over 5, because 12 would be higher based on how we drew it. We're going to have V2 minus V1 over 5, based on how we drew it, which is going to be equal to I3, which is going to be V1 minus the ground, which is 0 over 10. For node 2, let's write that. We're going to have 2 is equal to V2 minus V1 over 5, based on how we drew current 2, plus V2 minus 0, which is the ground, over 10. This is basically the hardest part, and you can get through everything just by simple math. So let's multiply both sides by 10 to get rid of the fractions. We're going to have 24 minus 2V1 plus 2V2 minus 2V1 equals V1. We're going to finish solving this. So we're going to see that this is 24 minus 4V1 plus 2V2 equals V1. We're going to add 4V1, subtract 2V2 from both sides, add 4V1, subtract 2V2. Then we'll get our first equation, which is 24 equals 5V1 minus 2V2. Let's do the next part. 20 is equal to 2V2 minus 2V1 plus V2. And then we're going to have 20 is equal to 3V2 minus 2V1. This is going to be our equations that we're going to solve our system of equations. First, we're going to use one step. We're going to solve for V2, and then we're going to plug that into the other equation. So let's start that. So here we have 24 is equal to 5v1 minus 2v2. We're going to solve for v2, so we're going to have 24 minus 5v1 equals minus 2v2. Divide everything by minus 2. Then we will have minus 12 plus 5 half v1. We're going to take this, going to plug it into this v2. Then we're going to have 20 is equal to 3v, no, put that in, 3 negative 12 plus 5 half v1 minus 2v1, 20 is equal to negative 36 plus 15 over 2v1 minus 2v1. So we'll have 56 is equal to 11 half v1, and then v1 is equal to 10.18 volts. And then by plugging this back into this equation, we will have V2 is equal to 13.45 volts. And then this is going to be our answer. I'll have Olivia walk you through the second step.
All right. So now what we're going to do is going to do a method that Dr. Pete likes to do in class. Basically, he has the currents pointing away from the node that we're at all times. So as you can see, the tail end is at the node that we're at, and the arrows point away. So that means that we're always going to start with V1 when we write our equation. So let's start node 1. So at node 1, we're always going to write V1. We're going to subtract the higher voltage, which in this case is 12, or the lower voltage, my bad, and put that over the 5 ohm resistor. Then we're going to do V1, subtract 0, our ground, and put it over the 10 ohm resistor. And then we're going to have V1 and subtract V2 and put that over 5 and set this all equal to 0. Now this is because we have I1 plus I2 plus I3 is equal to 0. Now we're going to do the same thing for this V2. So at this node 2, we're going to have V2 minus V1 over 5 for I4 plus V2 minus 0 over 10 for I5. And then we're going to subtract 2 because we're subtracting the current going this way, which will be the negative 2 amps, and so that all equal to 0. Now that we're here, we're going to do similar methods to what Chiamaka did and multiply the equations by 10 to get rid of the fraction. And so for the first equation, that leaves us with 2v1 minus 24 plus v1 plus 2v1 minus 2v2 is equal to 0. And for this equation, we're going to have 2v2 minus 2v1 plus v2 minus 20 is equal to 0. And then we're going to write this in the form where the constants are equal to the 2 unknown variables, and that gives us 5v1 minus 2v2, which is equal to 24, and that gives us negative 2v1 plus 3v2 is equal to 20. Now that we're here, we're going to do simple matrix math to help us solve for this. So what we're going to do is we're going to use the formula A, which is the coefficients of these two. The inverse of A times B is equal to the unknown matrix. So now let's see, what does that look like with the values filled in? So it's going to give us 5, negative 2, negative 2, 3. This is matrix A times the B matrix, which will have the coefficients 2 times 20. And that's going to be equal to our unknown matrix V1 and V2. Now that we have this, what we're going to get in our matrix is that V1, V2 is going to be equal to 10.18 times 13.45 using our matrix calculator, because we did the negative inverse of this one times this one is equal to this. So our final answer is V1 is equal to 10.18 volts and V2 is equal to 13.45 volts. And as you can see, that is exactly similar to the first method.
Yep, and that concludes our time domain analysis video. Hope you enjoyed.